Welcome back. Let's look at the graph of the equation y is equal to x in the 3 space. Um, so notice that the z coordinate here is missing. Um, so 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 what's the graph of this equation? Well, so basically then the graph would be the collection of all points in the 3 space whose first two coordinates will satisfy this equation. So again, the graph would be the set of all points in R3 such that the first two coordinates of the points will satisfy this equation. So put differently, we're looking for points in 3 space whose x and y coordinates will lie on this straight line in the xy plane. So in the xy plane, the graph of this equation is simply a straight line. So in the xy plane, so I have this straight line in the xy plane, the graph of y is equal to x. So now we are looking for all the points in the 3 space whose x and y coordinates will lie on this line. So obviously then from each point on this line, if you make a vertical line, then we will get the points whose first two coordinates lie on this line. So what we see then is that the graph of this is a plane that's going to be perpendicular to the xy plane, and it will pass through the line y is equal to x in the xy plane. So again, if we pick any point in this plane, then if I drop the plane, or if I project the plane onto the xy plane, if I pick any point on this plane, and then if I project it onto the xy plane, then I'm going to get a point on the straight line y is equal to x. Now the other thing to notice here is that the z coordinate here is missing. So what is the trace in any plane parallel to the xy plane? That is, what's the trace? In z is equal to k? Well, if I set z to be k in the equation, I just get y is equal to x again. So the trace in z equals to k is just a copy of this line y is equal to x. So in other words, so what we are getting is this straight line. So so when z is 0, you get the straight line y is equal to x, and then as z equals to 1, 2, and 3, and so on, you are getting the copy of the same line as the traces. So when z is negative, when k is negative, you also get a straight line that is a copy of the line y is equal to x. So traces in planes z equals to k are just copies of this same line. Okay, so I hope that you understand why the graph of this equation is this plane. Okay, now let's look at another example. So in this example, we are looking at the equation y is equal to x squared, and again this is an equation in x in the 3 space. So what's the graph? The graph of this equation in just the xy plane is a parabola. So we get a parabola in the xy plane, but we are looking for all points in the 3 space whose x and y coordinates will satisfy this equation. In other words, we're looking for points in R3 whose x and y coordinates will be on this will lie on this parabola. So then from each point on this parabola, if we make a vertical line, then we pretty much get all the points whose first two coordinates will satisfy this equation. So for example, if I pick any point on this surface here, on this curved surface here, so the curved surface goes like this. If I pick any point on this curved surface, let's say this is a point on the curved surface, then if I project it onto the xy plane, I should be getting a point on the parabola. On the other hand, I can also notice the following. Since again z is missing here, so the traces in planes z equals to k, that is traces in planes parallel to the xy plane, will all be copies of the same parabola. So this parabola. So when k is 0, we get this parabola in the xy plane, and then when we look at z is equal to 2 plane, then we are getting this parabola, z equals to 3, 4, 5, and so on. We are getting the same parabola as the trace. And then when k is negative, we will be getting other parabolas. So you can see that the graph of this is this curved surface. This is an example of a cylinder as well. Okay, so I hope you guys you understand why the graph of this guy looks like this. Okay, so I'll be stopping here, and in the next video we will be looking at quadric surfaces.